In a previous video discussing the weaknesses of electric systems, we explored how repeated energy conversions lead to efficiency loss. This time, let's examine railways from the perspective of energy utilization. The railway system transports goods by rolling steel wheels on steel rails, both made from hard materials. Because they are rigid, their contact surfaces exhibit almost no visible deformation, resulting in minimal rolling resistance when the wheels rotate. This contrasts sharply with vehicles using rubber tires, which deform significantly. Railways benefit not only from greater durability but also lower energy loss during travel. However, the lack of deformation reduces traction, making this both an advantage and a disadvantage for railways, which rely on high tractive effort to transport large loads. To counteract the negative effects of reduced traction, railway networks developed with low gradients, allowing heavy loads to be moved with less energy, thus maximizing low rolling resistance. Because of this, railways became the most energy-efficient ground transportation system, at least when operating on flat terrain at speeds up to several hundred kilometers per hour. To fully capitalize on this efficiency, rolling stock must also meet high energy efficiency standards. Initially, trains were powered by biological energy, horses and manpower, but rising transport demand led to the adoption of steam engines. Steam engines were extremely inefficient, converting less than 10% of coal's energy into useful work. However, they had the advantage of directly driving the wheels, making them highly practical for train operation and leading to widespread adoption. Meanwhile, electric motors were introduced to railways early. While they required reduction gears, DC motors functioned similarly to steam engines, capable of propelling trains without complex mechanical transmissions. Their high efficiency made them appealing, despite the challenges of electrification. Regarding energy sources, early electric railways outside regions with abundant hydropower still relied on coal. Coal was burned to produce steam, which powered steam engines that drove generators. The electricity generated was then transmitted over long distances to power electric trains, an indirect and complex energy transfer process. Despite this inefficiency, the system thrived because steam engines at power stations operated more efficiently than those used in locomotives. While boiler designs were similar, the methods of extracting power and reusing steam differed. In locomotives, the large onboard boiler limited the space available for additional components. Single sets of pistons were typically used, and spent steam was exhausted directly into the atmosphere. In contrast, power station boilers reused spent steam to drive secondary pistons, and in some cases, additional pistons or turbines, maximizing energy utilization as much as possible. Furthermore, the steam was collected and condensed back into water in a condenser, and the resulting hot water was returned to the boiler to recycle even the modest energy contained in its heat. While the thermal efficiency of a simple steam engine barely reaches even 10% at best, engines equipped with this system achieved efficiencies approaching 20%. Implementing such a system required more complex construction and additional space, but in power plants where equipment can be installed over a wide area, this was not a significant concern. In railways, there were attempts to incorporate multi-stage expansion mechanisms and condensers in steam locomotives. However, the resulting complex structures, along with the considerably larger equipment needed compared to a tender and various difficulties in securing cooling power, prevented these designs from becoming widespread, eventually giving way to the era of internal combustion vehicles. What about the transmission losses from the power plant to the locomotive? With AC power transmission, the current can be significantly reduced, enabling practical and efficient transmission. However, because railways operated on DC, as locomotive output increased, the resistive losses in feeder cables and catenary wires became substantial. As mentioned in the Ataya Pass video, the two EF16 units sometimes experienced a voltage drop of up to 500 volts. Furthermore, the DC machines of that era used resistor control, so that, except at specific speeds, they operated at efficiencies considerably lower than the optimum for electric motors, making it hard to claim that electric traction was inherently high efficiency. Assuming transmission losses of 10%, losses of 30% attributable to the locomotive's control system, and an electric motor efficiency of 92%, even if a power plant generated electricity at an efficiency of 20%, the overall system efficiency would be approximately 11.6%. This value is obtained by multiplying the efficiencies of the various stages, 0.2 times 0.9 by 0.7 by 0.92. In this case, the overall efficiency is not much different from that of a steam locomotive itself. Ultimately, however, commercial power generation became widespread, and its economies of scale allowed for inexpensive electricity, making the system viable. Of course, while the efficiency of steam engines improved by transitioning from reciprocating mechanisms to turbines, the fact that steam turbine locomotives equipped with condensers never became widespread further confirmed the efficiency superiority of electric railways. Today, in modern electric railways, power plants use combined cycle gas turbine and steam turbine generation, achieving generation efficiencies that exceed 60%. Moreover, in rail systems, especially in high-speed trains that demand great output, AC electrification has advanced, enabling high-voltage transmission. Advances in electronic technology have eliminated the need for resistor control in rolling stock, reducing thermal losses to less than 10%. As a result, no other mass transportation system currently matches its efficiency. When nuclear power was considered as an energy source, in the same era when nuclear-powered aircraft were seriously contemplated, it was also examined for railways, but the concept was never realized. Since power generation relies on steam turbines or gas turbines, it cannot overcome the inherent efficiency limitations of these methods. Recently, Mitsubishi's small modular reactor coupled with CO2 gas turbine generation has made headlines. However, even though the system is compact enough to fit on a truck bed, the electric motor it can drive produces only about 500 horsepower. Even if it is claimed that fuel does not need to be replenished for over 20 years, there is no practical merit in installing such a system on railway vehicles. For fixed installations there might be some viable applications, but when it comes to mobile vehicles, aside from auxiliary chargers for submarines, it is difficult to find any other useful application. There was a time when the synergy between renewable energy and electric railways garnered attention. However, converting renewable energy into electricity presents numerous challenges. Even if the efficiency of power generation itself were disregarded, the enormous energy consumption required to construct generation facilities, along with unresolved issues such as environmental pollution, remains problematic. Moreover, given the low energy density per ground footprint, especially under climatic and geographical conditions like those in Japan, this method is not one that should be broadly adopted. What about battery vehicles, which once received considerable attention? Although the issues with batteries have not yet been resolved and widespread adoption does not seem imminent, if a dream battery were developed that is lightweight, inexpensive, produces no hazardous waste, and is fully recyclable, the established conventions of electric railways would be completely overturned. After all, such a battery would eliminate the need for power supply equipment that has been indispensable since the inception of electric railways. Even today's efficient and high-performance electric railways continue to be challenged by this requirement. If an ideal battery were realized, these installations would become unnecessary and operating costs could be further reduced. Now turning to efficiency, battery systems might not intuitively seem efficient. Even the current mainstream high-efficiency lithium-ion batteries lose energy as heat during both charging and discharging, with total losses amounting to roughly 10 to 20%. Although new batteries exhibit even lower losses, aging degrades their efficiency, and temperature also plays a significant role. In low-temperature conditions, additional energy for heating is required to mitigate cooling effects, causing losses to escalate dramatically, a deeply troubling situation. While flywheels and supercapacitors do not suffer from these issues as severely, it is challenging to achieve the same capacity for an equivalent weight compared to lithium-ion batteries, rendering them impractical for railway vehicles. In view of this, even though lithium-ion batteries are only slightly less efficient than the traditional catenary system, if an ideal battery could be developed, there is a possibility that trains without catenary, thus eliminating the need for conventional overhead power supply systems, could suddenly become widespread. This would be especially disastrous for diesel railcars operating on regional lines. However, the prospect of realizing such an ideal battery remains remote, so for the time being, the status quo is likely to persist. A substance that occupies a role similar to that of batteries is the man-made material that might initially appear to be a fuel. Hydrogen and ammonia fall into this category, and while they have garnered some attention, and are sometimes confused with fuels such as diesel or gasoline because they combust, unless hydrogen becomes commercially extractable as a natural resource, its function remains essentially identical to that of an energy storage battery. From the perspective of vehicle applications, the rapid refueling speed is an advantage over batteries. However, aside from that benefit, there are countless challenges, and no clear prospect for economic viability exists at present. Furthermore, when it comes to so-called green hydrogen, its production demands an enormous amount of energy. If one attempts to utilize it as electrical power, its energy efficiency falls far short of that of batteries. Hydrogen production of this nature might be feasible in regions where renewable energy utilization is practical, but in other areas it would have to rely on nuclear power. For vehicle applications, this means that we must wait for nuclear fusion reactors, a medium for energy storage that is likely to become practical only in the rather distant future. Railways have experimented with and even prototyped fuel cell vehicles and hydrogen engine vehicles, but these efforts have remained merely investigations into technical feasibility. In the past, diesel and electric vehicles became widespread because they offered overwhelming performance advantages and superior economics compared to steam locomotives. The brief hype surrounding gas turbine vehicles was due to the expectation that their extraordinarily lightweight and high-output design could revolutionize the conventional norms for high-power locomotives and high-speed trains. Although railway vehicles powered by batteries, hydrogen, and various other synthetic fuels have attracted some attention in recent years, the reality is that none of these systems exhibit any extraordinary, standout capability. Moreover, a fatal shortcoming is that their performance, in terms of both output and speed, is inferior to that of existing diesel vehicles. In the railway sector, where speed and energy efficiency are paramount, any system that raises significant questions in both respects is ultimately deemed unsuitable. Even the much-anticipated linear motor Shinkansen exhibits interesting aspects from an efficiency perspective. In the past, maglev railways were promoted as exceptionally efficient because they employed superconducting magnets, essentially a type of permanent magnet, to achieve levitation, thereby eliminating the kind of resistance encountered with wheels and requiring no energy for levitation aside from that used for cooling. However, reality is far less ideal. While the vehicles are indeed equipped with superconducting magnets, the complementary magnets are installed as coils along the sides of the track on the ground. Not only do these coils serve to enable levitation, but they also determine the vehicle's direction along the track. A superconducting magnet travels along a series of these coils. As the magnet passes a coil, an electric current is induced within it, magnetizing the coil so that it either repels or attracts the approaching magnet. This force both lifts the vehicle and guides it in the predetermined direction. Certainly, on the vehicle side only the cooling power for the superconducting magnets is required. However, installing superconducting magnets along the entire track on the ground to achieve levitation would be prohibitively expensive. Therefore, as described earlier, coils are arranged along the track. When a superconducting magnet passes at high speed, its strong magnetic field induces electrical power in these coils by electromagnetic induction. In effect, it is as if power generators are distributed along the ground. Although they are termed generators, the coils form closed loops in a short-circuited state. The induced current is locally consumed, enabling them to function as magnets. Ideally, these coils would be constructed of low-resistance silver or copper. Even though both metals are less costly than superconducting magnets, their expense remains prohibitive. The cost of silver is astronomical, and copper is also very expensive. Consequently, a compromise was struck with aluminum coils. Although aluminum's electrical resistance is somewhat higher than that of copper, its cost is tolerable. However, increased resistance means that a larger portion of the induced current is converted into heat. This thermal loss ultimately adds to the power consumption of the driving coils used to propel the vehicle, thereby increasing the total energy required for operation. Unlike air resistance, it diminishes as speed increases. These losses represent an inherent drawback that contradicts the notion of maglev systems having exceptionally low running resistance. With conventional steel wheels, almost no power is needed to maintain the vehicle's position and direction. In magnetic levitation systems, however, this issue is unavoidable. Adding to the complexity, the powerful magnetic field of the superconducting magnets, which enables levitation, interacts not only with the coils but also with nearby metallic structures along the track, inducing eddy currents within them. The ground coils themselves, being composed of thick metal, generate eddy currents that do not contribute to propulsion. Consequently, the currents induced in various metal structures, such as reinforced concrete, are entirely lost as heat. The situation is even more critical for steel-framed bridges. Although the induced current decreases sharply with increasing distance from the superconducting magnets, a multitude of small metal masses can collectively result in significant, non-negligible energy losses. In the trials on the Miyazaki experimental line, it was found that this effect was unexpectedly large, prompting modifications to the track structure, materials, and construction methods. The running resistance generated by this phenomenon increases proportionally with speed, and at 500 km per hour, its impact becomes significant. In addition to the efficiency degradation inherent to the maglev system itself, the nature of these trains, mostly operating in tunnels, introduces further effects. Although measures have been taken, such as reducing the vehicle's cross-sectional area and enlarging the tunnels, the running resistance remains higher than that experienced by current Shinkansen operating outside tunnels. Moreover, during the brief takeoff and landing phases, the system employs rubber-tired running akin to that of an aircraft, which results in substantial resistance. Consequently, maglev systems exhibit an unusual running resistance curve that differs from conventional rolling stock. Even when operating at 300 km per hour, the same speed as current Shinkansen, the present linear system endures greater running resistance than the Shinkansen. Furthermore, efficiency challenges also arise from the linear motor drive itself. As mentioned in the earlier video on gas turbine linear motor cars, whether using induction or synchronous control, the onboard linear motors suffer from a wide air gap between the ground coils, serving as the stator, and the vehicle-mounted coils, acting as the rotor. Unlike rotating induction motors with precisely aligned rotor and stator components, the linear motor system designed to propel an oscillating vehicle cannot avoid this gap, resulting in a significant drop in efficiency. Including losses in the control circuits, the drive efficiency of Shinkansen is estimated at around 90%, whereas linear systems are said to achieve roughly 80%. Additionally, by design, train control in linear systems is affected by energizing ground coils along the track. Rather than being activated only over the section directly under the train, these coils are powered over a span roughly 3 times the train's length. This leads to considerable inefficiencies compared to the Shinkansen system, where only the train's electric motors require power. In the linear motor Shinkansen, although route short-circuiting and the brief high-speed operation are expected to reduce energy consumption per run, the combined effects of degraded drive efficiency in the maglev linear system and the increased running resistance from high-speed tunnel operation result in a significant impact. It has been estimated that electrical energy consumption per passenger may be several times that of conventional Shinkansen. Rail transport, long regarded as a continual progression toward reduced energy consumption, is now witnessing the linear motor Shinkansen set aside efficiency in favor of speed. The long-standing limitation of weak adhesion performance, which restricts acceleration, limits uphill gradient capability, and forces speed restrictions on downhill sections due to braking performance, has been a railway's fate. In ground coil linear systems, however, this issue is eliminated, providing high acceleration performance and superior climbing capabilities. Furthermore, due to wear on wheels and ground equipment, current systems find it challenging to attain commercially viable operational speeds exceeding 400 km per hour. In contrast, the linear motor Shinkansen targets a realistic operating speed of 500 km per hour, potentially creating a competitive edge over aircraft for transportation distances of up to approximately 1,000 km. However, from a commercial standpoint, regrettably, the only economically feasible segment appears to be the short corridor between Tokyo and Osaka. Moreover, when compared to ground-running linear systems plagued by the triple challenges of magnetic repulsion, air resistance, and tunnel resistance, aircraft, despite their inherent efficiency disadvantages related to gas turbine drive, may, in some respects, hold unexpected advantages. In reality, aircraft that employ high-output, high-efficiency gas turbines optimized for low temperatures at extremely high altitudes and which fully capitalize on the reduced air resistance at those elevations to minimize fuel consumption could ultimately be more favorable overall in efficiency than the linear motor Shinkansen. To reduce the significant air resistance encountered on the ground, the cross-section of the train body is considerably smaller than that of the Shinkansen. Additionally, the nose of the lead car is elongated. As a result, even with the same 16-car configuration, the seating capacity is expected to decrease by about 30% compared to the Shinkansen. Although it has advantages over aircraft, the energy efficiency per passenger is significantly lower than that of the Shinkansen. If the goal were to match the Shinkansen seating capacity, it would require either cramming passengers in like the third-class cars of the past or adopting a larger train body. Even though travel time is short, third-class seating is no longer acceptable in modern times. If a larger train body were used, increased air resistance would further deteriorate energy efficiency. Additionally, tunnel cross-sections would have to be redesigned, worsening economic feasibility. Perhaps the sense of security provided by ground travel will prove the most compelling advantage over aircraft, but it may only be when safety comparable to that of the Shinkansen is firmly established that the true value of the linear motor Shinkansen is recognized. The challenge of a new high-speed railway undertaken at enormous cost in Japan's limited territory is truly intriguing, and it remains to be seen what outcomes this endeavor will ultimately achieve.